Hello. In this video, we're going to look at logarithmic derivatives. In other words, we're going to find the derivatives of our favorite logarithmic functions. Now, to start off, we need to remember a bunch of rules for how exponents work, how logarithms work, all the things we learned in Precal. So, in particular, you might remember from grade 9 that we have these exponent rules. E to the power of x plus y could be rewritten as e to the x, e to the y. We use this rule in either direction. Either if we have the same base, we can add the exponents, or if we're adding the exponents, we can break it up to become multiplication with the same base. If you remember, when you're dividing exponents, we go ahead and actually subtract. So if we have e to the x divided by e to the y, and we have the same base when we're doing division, we can turn that into subtraction. And the third and most popular of the exponent rules, when you have power to a power, you multiply. So e to the x to the power of y is equal to e to the x times y. Now these three rules for exponents have similar rules in logarithms. It's a little bit different because, of course, they're logarithms, not exponents, but there's a bit of the same flavor. If you have the logarithm of x times y, then you can rewrite that as the logarithm of x plus the logarithm of y. Or, of course, go the other direction. If you're adding two logarithms, you can combine them using multiplication. Now, notice I'm writing these with ln because these rules work in general for any logarithm, but the main logarithm we're going to be focused on in this lesson and in most of calculus is the natural logarithm. Just in case you've forgotten, ln x means we are looking at log base e of x, the natural logarithm. And e right here is the special number that is approximately 2.71. So picking up with the next log rule, the natural log of x divided by y is equal to logarithm of x minus logarithm of y. If you're subtracting logarithms, you can go ahead and divide the arguments. If you have an exponent on something inside of a logarithm, you're allowed to take that exponent and move it to the front. It becomes a coefficient. Or the other way, if you have a coefficient, you can hop it on up and make an exponent. Now, another rule that's very important is the ability to convert between exponentials and logarithms. So log base b of a equals x would mean the same thing as b to the x equals a. The way I tend to remember this is the base becomes the base. So whichever way you're converting, your base will always be your base. And then the x pops on up to become the power. Or if you have the power, it pops on down to become the answer. As long as you can track those two, the a just fits in the remaining spot. So make sure, of course, you can convert between logarithms and exponentials. Now, a few more rules. We know that, as mentioned above, ln x is the natural logarithm, log base e of x. One thing you might need to know is if you're going to convert logarithms of different bases, if you had log base b of a, that could be rewritten as ln of a over ln of b. And a few important logs to know. Log base a of a is going to be equal to 1, so in particular, ln of e, because this would be log base e of e, will be equal to 1. Maybe another one that's worth writing down here is that log base a of 1 is going to be equal to 0. So in particular, ln of 1 would also be 0. Those are two important facts about logarithms, if you're trying to evaluate them, that are handy to know. Now we need to do a little bit of recall from Precal. How is the graph of ln x produced? How does this graph get made? Well, what we actually do is we have the original graph e to the x. That's where the natural logarithm comes from. We take this graph here in green, which is the graph of e to the x. And we take this line, y equals x, and we reflect it. We do the inverse. If you remember, when you're reflecting over the line y equals x, what you're doing is the inverse. And once you do the inverse of e to the x, well, you actually create ln of x. And so e to the x and ln x, how are they produced? Well, they're inverse functions of each other. ln x is the inverse of e to the x. It's the reflection across this line, y equals x. And this is actually going to be our definition for ln x. So you should copy this down. We have the definition. This is important again, definitions in mathematics. The definition of ln x. ln x is defined as the inverse of e to the x such that y equals ln x if and only if e to the y equals x. Now, we're going to use this definition to evaluate some basic properties. Let's say someone gave you ln of exp of x. Now, we need to just make a note here. Ln of exp means ln of e to the x. Sometimes mathematicians don't want to write e to the x all the time. E to the x, e to the x. It can look a little bit messy, especially because we have to have e to the power. There's that little superscript, and sometimes people want to write everything in one line. They don't want to have tiny letters up on the top. So if you're one of those people, you can write exp, which means e, and then bracket x means you're doing e of x. But either way you want to write it, ln of e to the x is just going to simply be x. Inverse functions, when you do f inverse of f of x, you always just get back to x. So ln of e to the x is simply x. Similarly, exp of ln x, or if you write it like this, e to the ln of x, is also equal to x. So what if you had exp of ln 7? Well, it's worth trying on your calculator. So if you have your calculator handy, go ahead and give it a whirl. Type in e to the ln of 7. You might have to type ln 7 first and hit equals, and then hit e answer equals. But you should get a perfect 7, which is pretty cool. To see your calculator get such a crazy decimal for ln 7, when you type in ln 7, you're likely getting some crazy number. But when you do e to that crazy number, you just get 7. So it's kind of neat. Now how about this? exp of 3 ln 2. Well, I kind of want to cancel the exp and the ln like I did here to just get a 7, but there's this 3 in the way. I can't cancel these. What am I going to have? 3, 2, 32? No, that doesn't make any sense. How can I get rid of this 3? Well, if I write it like this, and again, you might be more familiar by writing it e to the power of 3 ln 2, you might realize, oh, this 3 is a coefficient. It can hop up and become a power using my rules of logarithms. And then 2 to the power of 3, well, we know that that's 8. E to the power of ln of 8 is simply 8. Now for the last one here, ln of exp x cubed, this would again just be equal. If you wanted ln of e to the x cubed, is simply x cubed. So with that review out of the way, it's time for the main event. Let's try to do some calculus with logarithms. Rule number 1, which you should write down again, although it is in your notes, the derivative of e to the x is equal to e to the x. The proof for this was earlier in our notes. We used the definition of e as a limit, and we were able to find the derivative of e to the x was just itself, e to the x. Now, what do you think the derivative of ln x is? Think about it for a little bit. Do you think maybe it's just ln x again, like e to the x is? What could it possibly be? What would be the derivative of ln x? Well, let's see if we can come up with an argument, a proof. We're going to start by letting y equal to ln x. And unfortunately, I'm not able to do a derivative. I could write dy dx on the left-hand side, but then I'd have to do the derivative of ln, and that's what I'm trying to come up with. So we need some kind of trick. We need some kind of insight here. And what we're going to do is we're going to actually take e of both sides. Now, if I take e of both sides, I get e to the y, and on this side, I get e to the ln x. But e to the ln x is just x. And so by taking e of both sides, I've eliminated my logarithm. There's no more ln x. Now, I'm still going to have to do calculus. I haven't done any calculus yet, but I've been able to get rid of ln x, which is very useful because now I can use implicit differentiation. So when I do the derivative of the left-hand side, so now I'm going to do derivative. The derivative of e to the y is going to be e to the y times dy dx. The derivative of x is just 1. If I isolate for dy dx, I'm going to go ahead and get dy dx is equal to 1 over e to the y. But y, if we look over here, y is just ln x. So I have 1 over e to the ln x. And e and ln just cancel, so we get 1 over x. So the derivative, therefore, move this over a bit. Therefore, the derivative of ln x is equal to 1 over x. Let's go ahead and put that as our next rule, 1 over x. Wow, that's interesting. That's maybe not what you expected, but the derivative of ln x, we just proved it, must be 1 over x. So let's go ahead and give this a try. Do a few examples here. Let's find the derivative of ln 2x. Well, that would be 1 over 2x, then chain rule, so times 2. But wait a minute, that looks like we want to simplify it, right? We could write this as 2 over 2 to the x. You don't have to simplify, but it almost seems like you should. And wait a minute, we just get 1 over x. That's weird, that's strange. I thought the derivative of ln x was 1 over x. Why is the derivative of ln 2x also 1 over x? Well, let's look at our log rules here. Let's look at our log rules. If I had ln of 2x, I could write that as ln of 2 plus ln of x. Because if I'm multiplying, I can turn that into addition. So if I was going to do the derivative, well, I would get ln of 2. What's the derivative of ln 2? That's just 0 plus 1 over x, which just gives you 1 over x. Now, you don't have to simplify your derivatives, and you don't have to use log rule on any of them. If you were back over here seeing this question on a test or on an exam, you are more than welcome to box your answer right here. But I want to show you that you can still use log rules. You can still use all the algebra skills that you learned in Precal while doing calculus. And in particular, it helps explain why that 2 cancels. Now let's do another one over here. We have the derivative of ln x cubed. So let's see what we get. Well, log rule says you do 1 over x. In this case, you'll do 1 over x cubed times chain rule, 3x squared. Now again, you can box your answer. You can just leave it like that. Nothing wrong with it. But if you wanted to simplify, this is 3x squared over x cubed, which would be 3 over x. Strange. I wonder if we could show that using Precal. Let's try using some log rules again. We'd have ln of x to the 3, which would be, if we remember, this exponent can come down to become a coefficient, 3 ln x. So if we were going to do a derivative, we would get that 3 is a constant, 3 times 1 over x, which would just be 3 over x. So we get the same thing both ways. And again, that's the beauty of math. You can do something in 2 different ways and you'll always get the same answer. Of course, as long as you're not breaking any rules. So over here we have the derivative of ln sine x. Let's give that one a whirl. 1 over sine x times cos x. Again, always remembering to keep that chain rule in mind. Let's take a look at another rule. Let's find the derivative of a to the x. Now, we found the derivative of e to the x, which was e to the x, but this is a, where a is any number. So this might be, for example, maybe 2 to the x. What would be the derivative of 2 to the x, or 3 to the x, or 5 to the x? Well, maybe it's going to be like e to the x, so maybe the derivative of 2 to the x is 2 to the x, but if it was like that, why didn't I teach you the rule initially? If the derivative of 2 to the x was also 2 to the x, I probably should have included it when we learned the first rule for e to the x. So I don't think it's going to be that, but what will it be? Feel free to take a guess what you think the rule might be, and then let's try the proof. So we're going to let y equal a to the x. And then we need some type of insight, some type of technique here. And what we're going to do is we're going to take ln of both sides. So ln of y equals ln of a to the x. Well, if you remember your rules for logarithms, that x, it can come down. And instead of being an exponent, we can write ln of y equals x times ln of a. Now let's go ahead and do a derivative. So the derivative of ln y, we just proved, will be 1 over y times dy dx using implicit differentiation. Now how about the right-hand side? Well, the derivative of x is just 1, and ln of a is actually a constant, because a is a constant. So this is just 1 times ln a. Isolating for dy dx, we get dy dx equals y times ln a. Or dy dx equals y is equal to a to the x. So a to the x ln a. So therefore the derivative of a to the x is equal to a to the x ln a. Go ahead and put that up in your box. We now have a new formula, a to the x ln a. Let's give that a try on an example. Here we have the derivative of 7 to the x. Well, the rule says 7 to the x times ln 7. What about 14.3 to the x? Well, the rule says 14.3 to the x times ln 14.3. What about e to the x? Well, the rule says e to the x times ln e. Oh wait, you say, no, Mr. Peters, you shouldn't be using that rule here. We know the derivative of e to the x is e to the x. But that's okay. This rule applies for any base, and you can use it for base e, because we know that ln of e is simply equal to 1. So even using this rule here, kind of by mistake, because it's not really the rule for e to the x, but it is, because it'll be e to the x times 1, which is still just e to the x. Maybe this gives you a bit of better insight in terms of why is the derivative e to the x e to the x. It's actually e to the x times ln e. It's just that e is the special number that just so happens to give 1 when you do ln of e. Let's find another rule. This time for the log of any base. Just like we could find the derivative for any exponential, this would be the derivative for any logarithm. As an example here, what if you had log base 10 of x, your classic logarithm? How would you find its derivative? Well, take a guess. Maybe you think it's 1 over x. Maybe you think there's some type of ln business going on like with the general exponential. It's hard to say, but let's give it a whirl. Y equal log base c of x. It's hard to say what to do here, but the technique I'm going to recommend is change of base. So we're going to rewrite this as y equals ln x over ln c. Now let's go ahead and find the derivative. dy dx will be equal to ln c is just a constant, because c is a constant, so we write it as 1 over ln c times the derivative of ln x is 1 over x. So cleaning this up a little bit, we have 1 over x times ln c. And so therefore, the derivative of log base c of x is equal to 1 over x times ln c. There's our proof, and we can add that to our rule. Now this rule is very similar to the one for the general exponential. The general logarithm is the generalized version of just the natural logarithm. The natural logarithm has derivative 1 over x every time. If we have a different base though, like base 10, we have to put that extra little factor here, ln c, the logarithm of what the number was if it wasn't base e. So in this case, if we had base 10, we'd have to put 1 over x times ln 10. Now again, let's say you were doing this rule, and you forgot. You were doing the derivative of log base e. And you didn't realize that this was ln x. Well, you could use this rule, not a problem. The answer is 1 over x times ln e. But we know ln of e is just 1. And so you still get 1 over x. So again, you can use this general rule on the natural log, and it's not going to lead you astray. You'll get the same answer of 1 over x. It just maybe takes an extra step. So let's test drive our new rule on a few examples. Suppose we have the derivative of log base 2 of x. Well, we get 1 over x times ln of 2. Because we have base 2, we stick the extra factor of ln 2 on the bottom. So what if we have log base 10 of x? Well, that will give me 1 over x times ln 10. And this is actually why we use base e, not base 10 in calculus. Because I know you might have been used to saying, oh, log x in Precal, log x, and we don't write the base 10 because we know we're using base 10. It's the implied number here. You would have said log x. I love base 10. It just seems to work well for doing questions, and it does in some situations. But when you're doing calculus, if you just write log x all the time, whenever you have to do a derivative, you're going to end up with this extra ln 10 factor, and it's just messy. When you do log base e of x, like in the next example, you get 1 over x times ln e, which is just 1 over x. A much purer, a much nicer number. You might have liked log base 10 because you have 10 fingers, and sure, it's nice for base 10 and for counting in powers of 10, but in calculus, the best base for doing math is base e, because you just end up with 1 over x for the derivative. I know it's a little bit messy because you don't really have e fingers. It's hard to count in base e, but it's much nicer for doing calculus. Now let's look at the derivative of 5 ln x squared. Well, that 5, it's just going to come out as a constant. Then I'm going to do the derivative of ln x, which is always 1 over x, in this case 1 over x squared. Then I multiply by 2x. Again, you don't have to simplify your answer. This is good. All right, the derivative of 8 to the x plus 4x squared. Again, the derivative of a sum is the sum of the derivatives. So we do the first one, 8 to the x times ln 8 plus, well, this will just be 8x using the power rule. How about pi to the x squared? This one might be a bit tricky. So do your best. Take a guess on this question, the derivative of pi to the x squared. See what you come up with. All right, so the answer would be pi to the x squared times ln pi times 2x. Now, if you missed part of that, don't feel too bad. It's a tricky rule to learn. What we have here is something to the power of x. So you get that something to the power of x times ln of that something, and then you use a chain rule. This is sometimes how I think about the rule. If I have a to the something, the derivative is a to the something times ln a, whatever that a is, and then times the derivative of the something using the chain rule. All right, time for some multiple choice questions. Which rule is incorrect? Pause the video and make a prediction. All right, which rule is incorrect? Let's go through them. Rule A is the derivative of e to the x. No, that's a correct rule. That is correct. Let's look at the next one. Derivative of a to the x is a to the x over ln a. That is incorrect. The actual rule would be a to the x times ln a. But 1 over x is the derivative of ln x. That's correct. And for the logarithm, that is also correct. We don't have to use the letter c in the rule. We could use base b, and we could put a b down here. I just wanted to give you a base c to help clarify it from some of the other rules we're learning. But for this question, the correct answer is b. This is the incorrect rule. Determine the derivative of 3 to the x. I'll give you a moment to try it. Feel free to pause the video and make a prediction. All right, well, the derivative of 3 to the x, I think it's just the basic rule here. The derivative of 3 to the x is going to be 3 to the x times ln 3. All the other ones here are just crazy situations where they're really not following the rule. It's going to be ln. You always use ln, and then ln of that base. Here's another question. Determine the derivative of log base 3 of 3 to the x. Ooh, this one's tricky. Definitely pause the video and give it a try yourself. See what you come up with. All right, well, hopefully you've given this a try. The derivative, f prime x, would be 1 over 3 to the x times ln 3. Because the derivative of logarithm means you do 1 over what you have in the brackets here, and then times ln 3. Then we have to chain rule. The derivative of 3 to the x is 3 to the x times ln 3, which actually simplifies to just 1. So the answer is D. And another way to see this, if you're wondering, is if you were going to do precal on log base 3 of 3 to the x, you could write this as x log base 3 of 3, bringing down the power of x, and log base 3 of 3 is just 1. So this is x times 1, or just x. And of course we know the derivative of x. The derivative of x, of course, is just 1. Let's take a look at some more complicated examples. Here we have a product rule. So we have the derivative of log base 4 of x times sine of e to the x. Well, first off, we'll do the derivative of log base 4 of x, which is 1 over x times ln 4. And then we leave the sine e to the x. We leave that alone. Plus log base 4 of x times the derivative of sine will be cos. And then chain rule gives us another e to the x on the end. Let's do another one. The derivative of cosine inverse of tan of 7 to the power of 4x squared. My goodness, there's a lot of terms going on there. Well, let's see what we have. Definitely, we're going to do that inverse trig, which is negative 1 over the square root of 1 minus tan 7 to the 4x squared times, now we do the derivative of tan, which we know is secant squared, 7 to the 4x squared, times the derivative of 7 to the something is going to be 7 to the 4x squared times ln of 7. And then we do the derivative of 4x squared, which is 8x. So a lot of chain rule steps there, but as long as you follow the rules, you should get the correct answer. Now time for everyone's favorite, the quotient rule. Well, let's sing the song, low d high. So low sine of ln of 2x. So that's our low. d high. Derivative of 2 to the x squared will be 2 to the x squared times ln 2 times 2x less high 2 to the x squared. D low. Well, the derivative of sine we know is cos. So cos ln of 2x. And then we've got to use that chain rule. So the derivative of ln will be 1 over 2x. And then one more chain rule times 2. This is going to be all over the denominator of sine of ln of 2x squared. Now we'll look actually at an example exam question here. This is taken from an old exam. You can probably tell that this is taken from an old exam just based on the poor photocopying quality. So this is what they would ask you to do. Differentiate the following. Do not simplify. So let's give this a whirl. We want to find the derivative of, we have secant to the power of 4. It's always nice to rewrite that as secant of sine of e to the x to the power of 4. So we know we have that power rule first. 4 secant sine e to the x to the power of 3 times derivative of secant is going to be secant tan. So we get secant sine e to the x and then tan sine e to the x. Derivative of sine is cos. And then finally, derivative of e to the x is e to the x. Now it's good for you to have all your formulas in one place. So I encourage you to write down all the formulas for derivatives. We'll walk through these one at a time just so you have them all in your notes. We're done creating derivatives. These are all the rules that you're going to learn in this course. And so these are all the formulas for derivatives. We have the derivative of a constant is 0. The derivative of a power of x, you bring down that power, n x to the n minus 1. The derivative of sine is cos. Derivative of tan is secant squared. Secant is secant tan. Moving on to the next section. The derivative of cos is minus sine. The derivative of cotan is negative cosecant squared, and the derivative of cosecant is negative cosecant cotan. Now we, of course, have our good friends, the inverse trig derivatives. So the derivative of sine inverse is 1 over root 1 minus x squared. Tan inverse is 1 over 1 plus x squared. And secant inverse is 1 over x root x squared minus 1. These are the three main ones. When you go to do cos inverse, cotan inverse, and cosecant inverse, all three of these are just the negatives of the ones above. So the derivative of cos inverse is negative. Remember that negative sign because it starts with a c. 1 over square root 1 minus x squared. Cotan inverse is negative 1 over 1 plus x squared, and cosecant inverse is negative 1 over x root x squared minus 1. Then the new rules we learned today, the derivative of e to the x is e to the x. A to the x is a to the x times ln a. And two more rules. The derivative of ln x is simply 1 over x. And the derivative of log base c of x is equal to 1 over x times ln c. I encourage you to write these out at least once, maybe twice. We really want to get these derivative rules locked down, and I know this might seem like a lot to memorize, 18 rules, but in terms of an actual university course, memorizing 18 things is not actually that much. If you've ever taken a biology course, you know all the parts of the cell you might have to memorize, or all the parts of the body, all the parts of a digestive system, or a muscular system, all the different lobes in a brain. To memorize 18 rules, that's not actually too much. It's one of the things that I like about mathematics is you don't usually have to memorize too many things. We're mostly focused on process and technique versus actual memorization. Now one last multiple choice question for you here. If fx is equal to e to the x, determine ln of f prime of 2. Well, let's see. F prime of 2. F prime of x would just be e to the x. So f prime of 2 would be e to the 2. Well, what is L out of e to the 2? That's just simply 2. The correct answer is C. Make sure you take a look at your homework on page 223, number 2 to 33, and you can also look at chapter 3 review. You can do most of the questions in there now. Thanks for watching.